How the Price of Electricity Became the Structural Constraint of Industrial Civilization. A documentary script, 30 minutes, dated June 26, 2026. Act 1. The Invisible Tax. Every manufactured object on Earth carries a hidden price embedded within it, a cost that appears on no invoice, appears in no product description, and is understood by almost no consumer. That cost is electricity. Not the electricity used to power the factory lights or run the administrative computers. The electricity consumed in the actual molecular transformation of raw material into finished product. The electricity that splits chemical bonds, drives electrochemical reactions, and forces matter from one state into another. This energy cost is not a line item. It is baked into the atomic structure of everything we make. The modern industrial economy is, at its foundation, an energy economy dressed in the language of manufacturing. When an aluminum smelter in Iceland produces a ton of primary aluminum, roughly 15 megawatt-hours of electricity disappear into that single metric ton of metal. When a green hydrogen electrolyzer converts water into fuel, the electricity cost represents 60 to 70% of the total production cost. When a direct air capture facility pulls 1 ton of carbon dioxide from the atmosphere, the energy penalty is between 1 and 2 megawatt-hours. The product changes. The physics does not. Every energy-intensive industrial process is, at its core, a machine for converting cheap electricity into valuable matter. This reality has been structurally suppressed in mainstream economic analysis because for most of the 20th century, electricity was neither the dominant cost variable nor the strategic differentiator in industrial competition. Coal was cheap and abundant. Natural gas was geographically constrained but plentiful. Heavy industry located near fuel sources and built its supply chains around fossil energy. The price of electrons was a manageable input cost, not a civilizational constraint. That era is ending. As the global economy attempts to decarbonize its energy system, the industries that produce the materials of that transition, aluminum for electric vehicles, green steel for wind towers, synthetic fuels for aviation, green ammonia for fertilizer, are discovering that electricity is not merely an input. It is the input. And the price of that electricity is now the single variable that determines whether an entire industry can exist in a given geography. Act 2. The Electrolyzer Economy. The hydrogen economy is the clearest laboratory for understanding how electricity pricing functions as a structural constraint. Green hydrogen, hydrogen produced by splitting water molecules using renewable electricity, is the foundational feedstock for a cascade of critical industrial processes. It is the precursor to green ammonia, which feeds the world's crops. It is the reducing agent for green steel, which decarbonizes construction. It is the energy carrier for fuel cells powering heavy transport. And it is, critically, the primary input for the synthesis of sustainable aviation fuel through the Fischer-Tropsch and power-to-liquid pathways. The economics of green hydrogen production are brutally simple and brutally unforgiving. The levelized cost of green hydrogen is approximately 70 to 80% determined by a single variable, the cost of the electricity fed into the electrolyzer. At an electricity price of $100 per megawatt-hour, green hydrogen costs between $4 and $5 per kilogram, roughly 3 times the current price of gray hydrogen produced from natural gas. At $50 per megawatt-hour, the cost drops to approximately $2 to $3 per kilogram. At $20 per megawatt-hour, green hydrogen achieves rough cost parity with fossil alternatives. At $10 per megawatt-hour, a price point accessible only in the most resource-advantaged locations on Earth, green hydrogen becomes structurally cheaper than its fossil equivalent. This cost curve is not a projection. It is empirical. Electrolyzer capital costs have fallen by over 80% in the past decade and are expected to decline further. Stack efficiency improvements are approaching thermodynamic limits. The remaining variable, the dominant variable, is the electricity price. An electrolyzer sitting idle because grid power is too expensive is not a technology failure. It is a geography failure. The machine is correct. The location is wrong. The global rush to identify sites with sub-$20 electricity is not enthusiasm for renewable energy as ideology. It is an industrial calculation as cold and precise as the calculation that drove 19th century steel mills to locate adjacent to Appalachian coal seams. The energy is the business. Act 3. The eSAF problem. The case of electro-sustainable aviation fuel, eSAF, illustrates the electricity constraint with particular precision because the aviation sector has set the clearest and most legally binding decarbonization mandates of any heavy industry. The European Union's Refuel EU aviation regulation mandates that by 2030, 2% of all jet fuel consumed at EU airports must be sustainable aviation fuel. By 2035, that threshold rises to 6%. By 2050, it reaches 70%. These are not aspirational targets. They are legal requirements with financial penalties attached. The production pathway for ESAF follows a specific thermodynamic sequence. Renewable electricity drives an electrolyzer to produce green hydrogen. That hydrogen is combined with captured carbon dioxide, sourced either from industrial point sources or from direct air capture, in a reverse water-gas shift reaction to produce synthesis gas. That synthesis gas is then processed through a Fischer-Tropsch reactor to produce synthetic hydrocarbons, which are then refined into a jet fuel blend. The process is well understood. The chemistry is validated. Demonstration plants are operational in Europe and the United States. The technology is not the constraint. The constraint is the electricity price embedded in every step of this chain. The electrolyzer step alone requires approximately 55 kilowatt-hours of electricity per kilogram of hydrogen produced. A single kilogram of ESAF requires approximately 3 kilograms of green hydrogen. This means that producing 1 kilogram of ESAF consumes roughly 165 kilowatt-hours of electricity just in the hydrogen production step, before accounting for the energy consumed in the carbon capture, synthesis, and refining steps. Total system electricity consumption for 1 kilogram of finished ESAF ranges from 200 to 300 kilowatt-hours, depending on the carbon source and process efficiency. At a grid electricity price of $100 per megawatt-hour, a reasonable approximation for industrial electricity in Germany or the United Kingdom, the electricity cost embedded in 1 kilogram of ESAF is between $20 and $30. The current market price of conventional jet fuel is approximately $1 per kilogram. The green premium is not incremental. It is a factor of 20 to 30. This is not a premium that carbon credits, policy incentives, or consumer willingness to pay can bridge at scale. It is a structural cost gap that can only be closed by moving the electricity price down, or moving the production facility to a location where that electricity price already exists. Act 4. The geography of cheap electrons. The search for electricity below $20 per megawatt-hour is, in practice, a search for a very small number of places on Earth where natural geography converts renewable resources into electrons with minimal capital cost per unit of energy produced. These locations share identifiable characteristics. They possess either exceptional solar irradiance combined with minimal land cost, exceptional hydroelectric potential from high-altitude water systems, geothermal resources of sufficient temperature and volume to drive large-scale generation, or combinations of these resources that enable near-continuous generation without storage costs. The Atacama Desert of northern Chile represents the current global benchmark for cheap solar electricity. Irradiance levels of over 2,000 kilowatt-hours per square meter per year, combined with minimal cloud cover, extremely low land costs, and an elevation that reduces atmospheric attenuation, produce electricity from utility-scale photovoltaic systems at levelized costs below $20 per megawatt-hour. Several Chilean energy auctions have cleared below $15 per megawatt-hour. This electricity is not merely cheap by developed world standards. It is cheap by any historical standard for any energy source. Paraguay and Brazil's shared Itaipu hydroelectric dam complex produces electricity at an operating cost below $5 per megawatt-hour for the installed base, with expansion potential constrained by treaty rather than resource availability. Iceland's geothermal and hydroelectric combination delivers electricity at prices that have historically attracted aluminum smelters and data centers from around the world. Morocco's Atlantic coast combines solar and wind resources to produce blended renewable electricity that is competitive with any fossil alternative. What these geographies share is not political ideology, industrial heritage, or development status. They share a specific combination of natural resource endowment and low capital amortization cost per unit of electricity produced. The universal solvent, cheap electricity, is not manufactured. It is found. And the industrial processes that require it most intensely will, over the coming 2 decades, migrate to where it exists. Act 5. The stranded asset problem. The inverse of this geographic migration is the stranded asset crisis that awaits energy-intensive industries currently embedded in high electricity cost geographies. European industrial policy has spent the past 3 decades constructing an elaborate architecture of cross-subsidization, exemptions, and state aid to insulate its most electricity-intensive industries, aluminum, chlorine, steel, fertilizer, from the full cost of the energy transition. These instruments have allowed industries to remain competitive in the short term while deferring the structural reckoning. The reckoning is arriving through multiple channels simultaneously. European carbon pricing has pushed the cost of fossil-based industrial production steadily higher. The simultaneous closure of nuclear capacity in Germany removed the single largest source of low-carbon baseload electricity from the continent's industrial supply chain. The 2021 to 2022 natural gas price crisis, triggered by supply disruptions and then dramatically amplified by the Russian invasion of Ukraine, revealed how fragile Europe's industrial electricity cost structure had become. Aluminum smelters in the Netherlands and Germany curtailed production. Ammonia plants across the continent went offline. Zinc smelters in Belgium and Spain reduced capacity. These were not temporary shutdowns. Many represent permanent capacity reductions that have not been reversed. The economic logic is now irreversible for the most electricity-intensive processes. A European aluminum smelter paying 60 to 80 euros per megawatt hour for electricity is structurally uncompetitive with an Icelandic smelter paying 20 euros per megawatt hour, which is structurally uncompetitive with a hypothetical Atacama-based facility paying 10 euros per megawatt hour. No labor cost advantage, no policy subsidy, and no supply chain proximity can overcome a factor of 6 difference in the single largest input cost. The capital assets embedded in high-cost geographies are not merely struggling. They are becoming permanently uneconomic. For green industrial processes, electrolyzers, eSAF synthesis plants, direct air capture facilities, this geography problem is even more acute because these industries have no legacy fossil cost structure to compare against. They are being asked to compete not just against each other, but against fossil alternatives that have already fully amortized their infrastructure capital. A new eSAF plant in Germany competing against petroleum-based jet fuel is fighting a two-front war against the geological subsidy that makes fossil fuel cheap and against the renewable geography advantage that makes Atacama electrons cheaper. Act 6. The transmission problem. The obvious theoretical solution to the geography mismatch, transmit cheap electrons from resource-rich regions to industrial demand centers, confronts physical and economic constraints that make it, in most cases, financially non-viable. High-voltage direct current transmission lines can transmit electricity over distances of several thousand kilometers with losses of approximately 3% per 1,000 kilometers. The technology works. The economics do not, at the scale required. A transmission line capable of carrying 10 gigawatts of power from the Atacama Desert to the industrial centers of Europe would traverse approximately 12,000 kilometers of ocean and land. The capital cost of such infrastructure, including the offshore segments, the converter stations, and the land-based rights-of-way, would range from $15 to $25 billion per line. The amortization cost of that capital, spread over the electricity transmitted over the line's operational lifetime, adds between $10 and $20 per megawatt hour to the delivered electricity price, substantially eroding the geographic arbitrage that makes Atacama electricity valuable in the first place. This is why the more economically rational pathway, the one now being pursued by Morocco's X-Links project, Chile's hydrogen export strategy, and Australia's Asian renewable energy hub, is to convert cheap electrons into energy-dense molecules at the point of generation, then ship the molecules. Green hydrogen itself can be liquefied and shipped in cryogenic tankers. Green ammonia, which is simply green hydrogen combined with nitrogen, can be shipped in conventional ammonia tankers, an infrastructure that already exists. Green methanol and synthetic hydrocarbons can move through existing petroleum infrastructure. The energy content is exported. The electrons stay local. This molecular export model is not merely a workaround. It is a fundamental reimagining of what energy trade means in a decarbonized economy. Instead of shipping fossil fuels from resource-rich regions to energy-poor regions, the new model ships renewable energy in chemical form. The geography of comparative advantage in energy production does not disappear. It transforms. Saudi Arabia's advantage shifts from oil reserves to solar irradiance. Norway's advantage shifts from North Sea oil to hydroelectric capacity plus offshore wind. Chile's advantage shifts from copper extraction to the Atacama's electron factory. Act 7. The industrial policy response. Governments in high electricity cost geographies are not passive observers of this structural shift. The policy response has been aggressive, expensive, and, in the long run, likely insufficient to reverse the underlying thermodynamics, though it may slow and redistribute the industrial adjustment. The United States Inflation Reduction Act represents the most significant industrial policy intervention in American history, directing $370 billion in clean energy incentives over 10 years. The hydrogen production tax credit, the so-called 45V credit, provides up to $3 per kilogram of green hydrogen produced in the United States, contingent on meeting strict additionality and hourly matching requirements for the renewable electricity used. At current electrolyzer economics, this credit can bridge roughly half the cost gap between green and gray hydrogen at U.S. industrial electricity prices. It does not eliminate the gap. It narrows it sufficiently to justify investment in specific high renewable resource locations within the United States: the desert Southwest, offshore wind corridors in the Northeast, hydroelectric regions of the Pacific Northwest. The European Hydrogen Bank has committed 15 billion euros in auction-based subsidies for green hydrogen projects, with results from the first auction in 2024 revealing the depth of the cost gap. Supported projects required subsidies averaging 4 euros per kilogram to become viable, suggesting production costs of 6 to 8 euros per kilogram against a market price of fossil alternatives below 2 euros per kilogram. The subsidy is real. The underlying cost structure is unchanged. The political economy of these interventions creates a time-limited window. Industrial policy subsidies are politically sustainable when they support new industries in their early scaling phase. They become politically unstable when they are revealed to be permanent structural support for industries that cannot achieve market viability without them. The question that no government has yet answered honestly is whether the electricity price required for fully unsubsidized green industrial competitiveness can be achieved in high-cost geographies within the time frame of the political mandate. The physics suggests the answer is no. The policy continues regardless. Act 8. The temporal arbitrage. Against this backdrop of geographic constraint and political subsidy, a specific financial opportunity has emerged that sophisticated energy investors have been quietly exploiting for the past 5 years. The opportunity arises from the divergence between the long-term contracted price of renewable electricity and the spot price of that electricity during periods of high renewable generation. In power markets with high penetrations of solar and wind generation, California, Texas, parts of Western Europe, the spot price of electricity during peak generation periods frequently falls to 0 or below. Negative electricity prices occur when the supply of renewable electricity exceeds instantaneous demand and generators must pay to dispatch their power rather than curtail it. These periods of near zero or negative electricity are structurally predictable. They occur on sunny afternoons in summer, on windy nights in spring and fall, and during periods of low industrial demand. An electrolyzer or ESAF synthesis plant designed to operate with flexible load profiles, ramping production up when electricity is cheap and down when it is expensive, can achieve blended electricity costs substantially below the average grid price by concentrating its energy consumption in low-price periods. A facility that operates at full capacity during the 20% of hours when electricity is cheapest and at minimum load during the remaining 80% can achieve an effective electricity cost of 30 to 40% below the market average without any geographic relocation. This temporal arbitrage strategy has real capital cost implications. A facility designed for intermittent operation requires larger electrolyzer capacity per unit of average output, higher working capital for hydrogen storage, and more sophisticated process control systems. The capital efficiency of flexible operation is lower than continuous operation. But the operating cost advantage of very low electricity pricing, including negative pricing periods, can more than compensate for the capital premium, particularly as electrolyzer capital costs continue to fall and renewable penetration continues to drive more frequent low-price periods. The intersection of geographic arbitrage and temporal arbitrage defines the frontier of the green industrial economy. Facilities located in high solar or high wind geographies that can also exploit the daily and seasonal price cycles of those renewable resources. The Atacama's solar resource is not merely cheap on average. It is available in concentrated, predictable daily cycles that allow flexible industrial processes to optimize their electricity consumption against those cycles. Act 9. The second-order effects. The migration of electricity-intensive industry toward low electricity cost geographies does not merely relocate production. It triggers cascading second-order effects that reshape the entire industrial geography of the global economy. These effects are already visible in early form, and their trajectory over the next 2 decades will determine which national economies retain a manufacturing base in the decarbonized century. The most direct second-order effect is the relocation of downstream industries that depend on upstream green commodities. An ESAF production cluster in Chile does not simply displace jet fuel production from European refineries. It displaces the economic activity associated with operating the supply chain for that fuel, the shipping, logistics, and trading infrastructure, and creates new economic activity in Chile's Atacama region. Green ammonia production in Morocco does not merely displace European ammonia plants. It creates demand for engineering, construction, operations, and maintenance employment in Morocco, and reduces employment in the legacy European fertilizer industry. The second-order effect on energy security is equally profound. Nations that currently import fossil fuels to power their economies face a strategic choice: continue importing energy in fossil form and bear the transition cost of decarbonization, or develop domestic renewable resources that can reduce import dependency while supplying local green industrial production. This calculus differs dramatically by geography. Japan, which imports over 90% of its energy, faces a fundamentally different strategic position than Australia, which has renewable resources capable of supplying many times its domestic demand while exporting the surplus as green hydrogen to Asian markets. The third second-order effect is the redistribution of the fiscal base of energy exporting nations. Saudi Arabia's Vision 2030 is, in its energy dimension, an explicit acknowledgement that oil revenues will decline and must be replaced. The replacement strategy involves converting Saudi Arabia's solar resource, among the most abundant on Earth, into green hydrogen and green ammonia exports, preserving the kingdom's role as an energy exporter while transitioning the export product from fossil to renewable. This is not philanthropy. It is the most rational industrial strategy available to a nation whose comparative advantage is extreme solar irradiance rather than petroleum reserves. Act 10. The closing argument. The universal solvent thesis is, at its core, a claim about the structure of economic reality in the decarbonized century. It argues that the price of electricity is not merely one variable among many in the cost structure of green industrial production. It is the variable, the dominant variable, the variable that determines viability, location, scale, and strategic advantage for every energy-intensive industry that intends to operate in a net-zero world. This claim has a specific and testable implication. Industries that fail to secure access to cheap electricity, whether through geographic location, long-term power purchase agreements, or temporal arbitrage strategies, will not merely be less competitive than rivals who succeed. They will be unable to produce their products at prices that markets can absorb without permanent structural subsidy. The economics of green industrial production are not like the economics of software, where network effects and learning curves can drive costs to near zero regardless of geography. They are constrained by thermodynamics. The electrons must be cheap. That is not a preference. It is a physical requirement. The optimistic reading of this constraint is that the Earth possesses more than sufficient renewable energy resources to power a fully decarbonized global economy at costs that make every critical industrial process economically viable. The Atacama alone could supply Europe's entire energy demand. The global technical potential of solar photovoltaic is measured in hundreds of terawatts against a global demand of less than 30 terawatts. The electrons exist. The question is whether the capital, policy, and infrastructure systems can be assembled quickly enough, and in the right locations, to convert that physical potential into industrial reality within the 2-decade window that climate science suggests is available. The pessimistic reading is that the concentration of cheap, renewable electricity in specific geographic locations creates new forms of industrial dependency that replace fossil fuel dependency without eliminating the underlying vulnerability. A green hydrogen supply chain that runs from the Atacama through Chilean ports to European industrial facilities is not, from a supply security standpoint, categorically different from a natural gas supply chain that runs from Siberia through pipelines to German factories. The energy source has changed. The dependency has not. Both readings contain truth. The resolution lies not in choosing between them, but in understanding that the physics of cheap electricity defines the boundary conditions within which all other choices about policy, investment, technology, and industrial strategy must operate. The universal solvent does not care about ideology. It does not respond to political mandates or corporate sustainability commitments. It responds to the laws of thermodynamics and the geography of renewable resources. Every ton of ESAF, every kilogram of green hydrogen, every metric ton of green steel produced in the coming century will carry embedded in it a specific electricity cost. The nations and firms that minimize that embedded cost will dominate the industries of the decarbonized economy. The ones that do not will watch their industrial base dissolve, not in a dramatic collapse, but in the slow, thermodynamically inevitable way that ice dissolves in water. The universal solvent works not through force, but through persistence. Given enough time and the right conditions, it dissolves everything. That is not a threat. It is the operating principle of the next industrial age. End. Methodological disclaimer. Dated June 26, 2026. This documentary script synthesizes publicly available research on renewable energy economics, industrial decarbonization pathways, and green hydrogen cost structures. Statistical references draw from the International Energy Agency, BloombergNEF, the Hydrogen Council, the International Renewable Energy Agency, and peer-reviewed literature on electrolyzer economics and sustainable aviation fuel production pathways. Named geographies, technologies, and policy instruments are drawn from public sources. This documentary's contribution is the analytical synthesis, the connection between electricity pricing, industrial geography, and the structural constraints of the green industrial transition. Dated June 26, 2026.